extreme privilege and honor to be today with you and present the topic about column store indexes, especially the cluster column store one, which I am a big fan of. I think that this scenario of using those kind of indexes is way much probable than hackathon, which is suitable for quite different workload and types of scenarios. So it's 9 a.m., so we can start. 2 slides, one about me. My name is Damian Widera. I come from Poland, from south of Poland. And since 7 years I think, I am an MVP. And also I am a leader of Polish SQL Server user group, which is located in Wrocław. And the next 30 seconds, I would like to tell you about the conference that will be taken in Wrocław. I was asked if I can do so, but as it is a community event, I can do it. So if you wish, I invite you in May, 11 to 13. It's Monday till Wednesday, and you will have a chance to meet Adam Mechanic, which will give us a one-day workshop. Alberto Ferrari and Klaus Aschenbrenner are with us today in the conference. So if you wish to meet them in Poland, you can come. So probably half sessions will be taken in English. So if you wish, you can come not only in Polish. So, okay, I try to start this presentation once again. So as I told you, I come from Poland. I wrote a book about SQL Server, but this is unfortunately in Polish. So despite the book is great, I think you can't read it very well because, you know, Polish language is some kind of hard. Please visit my blog if you would like to read about the latest, newest thing about SQL Server. Of course, you can drop me an email afterwards, after the session. It would be great to have your opinion also. So let's go to the agenda. I would like to share my knowledge and experience about those types of indexes, column store indexes, especially the clustered column store index. I'm using the column store indexes since 2012 with my customers when they appear in the SQL Server 2012. In 2014, we started to use the cluster column store index because of their benefits they gave us. So I think that this topic and my experience is also worth to share with you. So you can start using those indexes, I think. So from my point of view, I'd like to concentrate on 3 important views. The first one is how to load the data efficiently to this column store index. The second topic is about how to use it efficiently. And the last one is about maintain them, the indexes. So at the last point, the very, very last point is about internals of such indexes. At the beginning, let's start and let's do a quick recap. You can find a very great article under this address. And basically, I think you already know it, but I'd like to set the baseline right now. So the column store indexes works in that way that this is a totally new storage that was done by Microsoft. We are very familiar with the row storage and B-tree indexes. And for column store indexes, everything is done differently. So the storage is flipped. So we do a turnaround. We take about 1 million of rows, from the traditional storage. We compress it, we encode it. The compression phase is a 6-step phase. And then we create something which is called a dictionary, which helps us in compression. And also we have something which is called a segment. A segment is essentially a column. So we store data in column and not in a row. And then we create and we store everything as a varchar, as a blob, so that we can access the query. The query can access the index using something which is called segment and column elimination, which I'm going to talk in a moment. So in 2012, we had this part. So we had row groups, which were compressed. So each individual column is compressed, and this is an equivalent of about 1 million of rows from the traditional storage. These groups are immutable. That means that after you compress it, you can change it. That's why in 2012, the non-cluster index was read-only. So when everything is compressed, the data cannot be changed. And in 2012, we had to drop the index, load new data, recreate it again to make sure that we can load new data to our data warehouse. In 2014, when a cluster Columnstore index appeared, there was a need to create two separate, let's say, object or structures. The first object is the delta store, which is the place where new data come, because cluster index must be updatable. So when new data come to a delta store, and they are stored there until they become compressed. And about this process, I will talk to you in a moment. The delete bitmap is important because of the delete process, how to make a delete from a compressed group which cannot be changed. And you have to delete somehow data from the index, because Columnstore index must be updatable. So the last slide about the beginning of the index is how it works. In my opinion, the winning point in the Columnstore index is essentially how it works on metadata. So first, if we have a query, it's a very typical query from data warehousing. So we have some key, we do some aggregation. So in traditional approach, we would have to read all data from a page. Even from the column, we really don't need in the query. In our case, we have 6 columns here in our storage. And really, we need that one, product key. We really need the sales amount because we are doing some aggregation on it. And there is a filter. And with Columnstore index, first of all, we eliminate the columns that are not needed in the query. And after all, we do a segment elimination, which is connected to this point. So we are filtering. So if you take a look on the picture, you will see that before we actually start the query, we eliminated on the metadata level the unneeded groups. That's why the index is working so quickly. That's one part of this. That's one part of this. Okay, so that's the beginning and that's the recap. Let's now go to the details. How to load the data efficiently and not get into the troubles. I did some tests in my environment when the index first was available. So I think that when you load data to the data warehouse, you can have one of those 5 scenarios, mostly one of those 5. So the initial situation is that if your table is a heap essentially, and you have to load data, so you can do basic insert and select statement and then create this Columnstore index. You can use bulk load method on the heap, and you can use the select into, which in SQL Server 2014 is a parallel operation at last. Or the other situation is that your table already has this Columnstore index, so it's not heap anymore. And then you can use insert select or use bulk load. So that will be my first demonstration, but don't worry, I will not load data because it would take me the entire hour, but I will show you the result and I will show you some implications. Please remember those 2 numbers. Those are magic numbers. The first one was first introduced by Nico Neugebauer, a SQL guy from Portugal, which is also fascinated in the same great deep level as me with these Columnstore indexes. So everything I found, I compared with his foundings on his blog. I will show you the resources later. So Nico first described this magic number, 102400, please remember it. And there is also the second number, 1048,567. It's also very, very important if you are going to load your data efficiently. So let's check it out. What's that? I hope you can see my screen. So let's go to data loading. First, in the conference material, you will find how I make AdventureWorks data warehouse database bigger. I use script that Callan Delaney has on her blog. I will attach the script to the conference material. So now I have one table which has over 30 million of rows. It's not a big one, but it's big enough to see some things that I'm going to show you. Apart from many enhancements that come in 2014, you should see that, or maybe you should even remember that in 2012, to work with Columnstore index very efficiently, sometimes we have to rewrite a query. And for example, very simple query that should give you only, summarizing one attribute or one fact. This simple query had to be rewritten to something like this. Otherwise, your index was not kicked to run in a batch mode, which is essentially what is this designed for. Batch mode means we take 1,000 row and put it into the memory. A traditional row store means that we take one row and process it, So here, all the rules are changed, and we take 1,000 row and put it to memory. So if we had this query in 2012, if we would like to have the benefit, it must be rewritten to something like this. So it was sometimes not so useful to change your reporting query, essentially. In 2014, everything has changed, and now we can use, and now we don't have to rewrite the queries. Okay, what about data loading right now? What else has changed? If you create a cluster column store index, you no need to have any other indexes. What's more important, you can't have them. So please forget about primary keys, foreign keys, check constraints. Everything that materialized to index cannot be used with cluster column store index. If you need them, create this key and create non-cluster column store index. Okay. We have really better performance about hash join. If something is going to spill to TempDB, it will be done in batch mode. So it's very important in terms of speed. But there are still some operators that are not working in batch mode. So watch out for distings and union, everything that do a distinct row. Okay, I check my environment right now. I hope it's configured. So this is the first scenario. So I'm creating a heap. I'm loading this magic number of rows to a heap. Then I create a cluster column row index, and I'm trying to find how much time does this operation take. This is the first loading. And on my computer, it was about 14 seconds. This 1 million of rows. Then I do the same, but I loaded data using bulk load API. So this heap plus loading data plus creating this index, and it took 19 seconds. Then I created a heap and used select into, which is a parallel operation, and it took 13 seconds. It's just for comparison. So that was essentially the first scenario when I'm starting from the heap. The second scenario was that I'm already starting from a table that has column store index, and then I'm loading the data. And it took only 8 seconds. And after this, I created the last scenario. So a table has already cluster column store index, and I'm loading data using bulk load API. So let's say normal operation. And it took 11 seconds. So if we only take a look how speed it can be, so the benefit is to create an empty table, create a clustered index on it, and then load data. However, the recommendation that was given by Remus Rusanu, who works in Microsoft on Service Broker, and I believe also did something about this column store indexes, is that he thinks and he recommends this situation, because then you can create better dictionaries. So I'm trying to use as much as possible those, but the recommendation is to do that way. But I will show you that whatever method you use, it's not important because now we have to go to the details. Assuming we have already data in place, we loaded our data successfully. So let's try now to take deeper into the tables. If we create a cluster index, we choose the clustering key. This is what the cluster index is all about. We need some cluster key. Right now, as you can see here, I have no chance to specify the clustering key. So my data are essentially unsorted there in this index. You know that clustered index is sorted on clustering key. So how can I sort this index, this particular index? I will show you that. Why it's important? If we see how is the data distribution in our index right now, so you see that we have this column number 4, which is the very interesting column for me. It's ship date key. I would like this column to be a clustering key. You see that this column is spread into 7 segments, and some of them have this magic number of rows, some of them, however, not. And what can you see here is that every segment starts from the same date, and every segment finish in the same date, which is not very good situation, because what I can't do right now is I can't do this segment elimination. I show you on the query that if I'm entering a filter, I'm issuing a filter, I would like to eliminate segments before I start the query. It's not possible right now. Data were loaded, one of those 5 scenarios, and I have situation which is not very comfortable, because essentially it is not working like I expect. So this is a problem number 1, and this is a problem number 2. And I would like to explain why we have something like this here. So why it's not the, let's say, magic number of rows, but something else. So how to fix the problem number 1? To fix the problem number 1, okay, I will show you that essentially now the segment elimination is not working. So to do so, I'm creating a new log, SQL Server log, not transaction log. I'm using a flag, trace flag undocumented but safe, which is called 646, which will send information to the SQL Server log about segment elimination. Okay? And I do a reporting, let's say reporting query. So in that case, I'm going to pick a date which is from the July 2008, and if we go one more time to see the data distribution, so you remember that it is everywhere. It's in every of those columns. So my query will not take benefit from the segment elimination. So if I do this query and I read the log, so I should see that nothing come here. So there is an indication that I really did issue the trace flags, so they are active. However, no segment elimination occurred. So the query could be slower. So how to make it faster? How to sort the data in cluster Columnstore index? So to do so, there is only one way to do so. First of all, you have to create a traditional clustered index on a column you need, column or columns you need. This traditional index, normal, typical B-tree index. Then you somehow load the data. The loading scenario is up to you. You have to have traditional clustered index in place. And then you have to create a Columnstore index with dropping the existing cluster index. However, it will not solve the problem number 2. The problem number 2 was that some of the groups have this 1 million rows and some of them have less than 1 million rows. That was because this operation was done in parallel. So if we do a parallel, the set of rows was taken by all 4 cores I have. I created as much groups as I could with this, let's say, magic number, and the remaining rows was spread into all cores, so smaller groups were created. So to avoid this, you have to do this operation like this. So create Columnstore index with drop the existing clustered index on one core, which this scenario maybe is not so good because this operation will take longer and longer. But let's look right now how our data distribution looks like and see. Now we have something I would like to have. I have something like this. I have no overlapping row groups right now. So if I take date, which is from July, I should see the data are taken only from this range. So 4 row groups should be eliminated before I actually start the query. And this is what I'd like to show you in the next query. So let's do a query right now. And let's check the error log. And you see they are really rows that were skipped. So my data was in the last row group, which was row group number 4. And you see the row group number 0, 1, 2, 3 were eliminated before we actually start the query. But it was done because I created the index using the max.poe equals to 1. Okay. So the first magic number is this 1048576. It's the maximum capacity you can have in the row group. If the row group is around 1 million row, it will be compressed. So first, if you load the data, the row group is open, and then if you are close to this maximum number of rows, 104876, the row group becomes compressed and is stored, and you can query it as a column store. Open store is a normal bit tree. So if we come here once again, so please remember on this screen that this is normal bit tree. So every query that touches this region is slow. So you have to take care, and every your data after you load it must come to this area because those data are compressed. So that's the important information. The second number of rows, the second magic number was described by Nico Neugebauer when he was experimenting with bulk load API. And for bulk load API, the capacity of the Delta store is around 100,000 rows. So he checked it, and he found that if he load the data to this group, so I'm loading 100,000 row right now from my disk. So you see that what I have right now from Columnstore row description dynamic management view is that I have one row group with 100,000 rows in it. But if I load 105,000 rows to my table once again, what should I see? I should see that one group is compressed, but the other one is still open, because the maximum capacity of this group is over 1 million row. But if you use bulk API, it's something more than 1,000 row and smaller than 105,000 rows. So Nico found that the magic number is something like this, 102400, and this is the border. So if you are using bulk load API, you should try to have to load more rows than this number. So what will happen if I load 100,000 rows again? There are 3 possible scenarios. A new open Delta store will be created. A new will be created here. Who votes on that? No one. I will have 200,000 row here. Who vote on that? And I have some third scenario, and I don't know which could it be. Okay. So let's take a look. So the second scenario is correct. As the group have only 100,000 rows, so I loaded the next 100,000. It's less than the maximum capacity, so I can put data here. So, as I told you, having opening delta store is not very good, so I will tell you in a moment how to fix that. So, let's go now to the maintenance part. So, you see that loading the data is one part, and after you have to rebuild your index if you would like to have the segment elimination, and I shown you how to do that. What about maintenance? It should be somewhere here. Okay, this is the maintenance. Let's go to the index usage. The maintenance is the third step. So in the index usage, as you know, this Columnstore index was said that we should not use it in OLTP scenario. But have you asked why? Because maybe we can. And it's only, a marketing stuff. Don't use it because we have a special index to OLTP scenario, which is called hackathon. So, and I will show you why it's not suitable to OLTP scenario. What is best to the index? Use update, merge, or insert plus delete statements. What is faster? That will be the second point. What about transaction support, third point, and partitioning, the last one in index usage as the point number 4. So, index usage. Why should not we use it in the OLTP scenario? I create a table, and I'm going to load 1,000 rows into it. So, we have open data store right now. I'm starting transaction and loading 10 more rows to my table. Transaction is open, and from other session, I'm trying to read the data. And the session is waiting. I can't read. Why I can't read? So maybe the query should be done something like this, without this predicate. Still waiting. New session. Maybe something like this, without this predicate. And we're still waiting. So when you open a transaction and you do an insert, the transaction is open, you do an insert, you issue an exclusive lock on the entire row group. You see, this is the first transaction, and there is an exclusive intent lock. So anything what is incompatible will have to wait. So in OLTP scenario, when you are loading that, you would like to do some insert or some changing data, anything that try to read, have to wait until you finish your transaction. And this is why the index is not suitable to OLTP scenarios. It's not anything else but only this. Okay, so let me finish my transaction. And let's go to the second point, which is update. Update merge, we can put merge also here, or delete plus insert. Let me close this unnecessary sessions. So what is faster? Let me check if I have the table. No, I haven't. I'd like to load this 1 million rows to my table to make sure that the open store will be compressed, because the operation is going to take place on the compressed store. And I try to make, let's say, massive update. I'm going to update 1 million row to some value. So let's do it. How long does it take, do you think? I have time to drink something. 33 to 44 seconds, depending of how speed is my laptop. So we'll see. Then, what I would like to do is I would like to query the Columnstore row groups data view to show you what happened. But if we can go to this screen one more time, how the update process is done. The update process is done in that way that you can't physically delete data from this row group. So you can only mark that data should be deleted. and this mark is done here in the delete bitmap structure. So it's some kind of soft delete. And the data will be deleted after you issue an index rebuild later. So you do essentially a mark here in this delete bitmap structure that data should not be taken into consideration. So it's the delete part from the update process, and then you have to insert data to the delta store to make sure that update was turned into delete and insert. Remember that everything that touches this point is very slow in comparison to row groups, to compressed row groups. So the process is done, 34 seconds. So let's mark the number here, 34. And right now, we do the same operation, but using index, using the delete plus insert. And we will see the result. It's there. It's there. So we'll see if this technique is more efficient or not. So I explicitly say delete and insert the data. So we check it. So it should give you information how to work with it. Please remember, in both cases, I will show you what happened in both cases. You see the delete was 5 seconds, 6.8 was the insert, so in total we have 12. So we have 12 in comparison to 34, I believe. So what is going on here? In both cases, it's the same. No, it's not the same. In the first case, we would see that this group is not compressed, it's opened. So the update process deleted 1 million row from the row group and create an open delta store. However, the delete plus insert created a compressed data store in my situation. So that's the desired state. I have already my rows compressed. So from performance point of view, this is what I would like to have. So you have to take into consideration that point also. What about transaction? Everything is permitted apart from transaction isolation level snapshot. You can't use it. So we can set it. We can even create a table. We can create a clustered index. But that operation is not allowed. So loading data in the transaction isolation level snapshot is not permitted. So you have to choose the other transaction level that are possible if you would like to load data into the cluster column store index. What else is possible? You can influence your optimizer by setting some special rules. The rules were described by Paul White and Benjamin Nevares on their blog. So there are two rules, enforce batch and enforce row, and you can use it on your query level. For example, in the select, at the end of the select, you should write an option, state that you should recompile. That means you generate a new plan, and then you turn on a rule, which is, for example, called enforce row. That means that your plan will not use the batch mode, but row mode. Or at least the optimizer will try to do this. But please be very careful with that, because if it's not possible, for example, if it's not possible to enforce the rule, your query will not finish and you will have an error. Okay, partitioning. You know, when you have cluster column store index, you should also think about two other things. Partitioning, which I think you know, and the second thing is resource governor, which I'm going to talk in a moment. Partitioning is enterprise feature, column store is enterprise feature, and resource governor is also enterprise feature. So you have to have enterprise edition to use the column store, so why not to use partitioning? And I'm going to use it. So I already created a table which I'm going to partition. Data in this table are from the year 2005 up to 2008 right now. So I created, let's say, 5 partitions to make sure that new data, if arrive, will go to this very latest partition. So first I created file groups, then I assign a file to each file group. I created partition function on my, I create partitioning schema. So right now I stick my file group to a particular ranges, and then I'm going to create a cluster column store index on that partition, on that partitioning schema. And this is what is not permitted. So if you try to make it done, you will see that create index statement failed because column stored index must be partition aligned with the base table. Wait a moment, my base table is a heap right now. So this message is some kind of wrong. This message is okay if you are created non-cluster column store index. So how to create the cluster column store index? The same approach like before. We have to create a normal, regular column store index on the column we would like to partition using the given partitioning schema. Having this done, we have to create a cluster column store with dropping the existing clustered index. And this will work. This is how partitioning should be done using cluster column store index. So do we have partitioning right now? Yes, we should have. We should have 5 partitions. The very last partition is empty right now. So I would like to check if my query works. I would like to show you how the data is distributed in the partitions. So we see that this is the partition number 1. It has 80,000 rows. The partition number 2 is a little bit bigger. It has 200,000 rows or more. And the data distribution across segments and partitions, you can check it out later using this view I'm presenting right now. But what's important, if we do the query and we have prepared our column store index, it should be, of course, I should write that the maxdop is equal to 1 here. So to make sure that my data are distributed properly across the segments. So if I run the query I shown on previous demo and I do the read error log, so I will also see that my partitions are, that I'm reading data from proper partitions and also that my segments are eliminated. So if I try to, what I'm trying to do is I'm trying to find where are my data taken from. So also with partitioning, the segment elimination works properly. So please remember that. So now let's go to the maintenance because we have only 23 minutes and I would like to finish on time. So how to maintain the index and the concept of tuple mover will be revealed. What to do, reorganize or rebuild the index is the second topic, and extended events, a great monitoring tool. You should be very familiar if you would like to monitor the column store indexes. You should use extended events all the time. So let's go to maintenance. What is tuple mover? There is a process that closes the delta store and do the compression and put data as a row groups. It wakes on every 5 minutes. It picks an open delta store 1, do the compression, and waits 15 seconds and pick another delta store, open delta store. So you know, within the 1 minute, you can have 4 or 5 delta store closed only. So it's not, the process is not very fast. There are reasons behind that, because you know the compressing data is a processing intensive process. So your CPU will be burned for seconds. That's why Microsoft decided not to make a full power tuple mover. It must be your decision to do so. And I will show how to run the tuple mover on full power. First of all, you can turn the tuple mover off by using documented trace flag 634. So if you run this global flag, the tuple mover will not be running, and you have to take care about it yourself. How to use it? Okay, let's do a table, let's do a cluster index on it, and let's load 100,000 row into the table. Invalid object name, okay, sure it's invalid. Now it should work. What we will see is right now that we have one open delta store. It has 100,000 rows. So as a tuple mover is right now not disabled, if we wait 5 minutes, it should check, but this and try to compress if the delta store is, of course, above the limit. We can try to reorganize the index, but this operation, written that way, will not close the open data store. So, if you would like to run the tuple mover manually on a full speed on all open delta stores in a moment, you should issue the reorganize the index and use undocumented option which is called compress all row groups equal to on. That means if I run this, okay, you see my delta store is right now compressed. So this is manual action of tuple mover, but running on all data stores in the same moment. So I think you should be familiar with this reorganize compress all row groups option. Of course, you can rebuild the index and rebuild closes everything and rebuild the new fresh copy of the index. So also take care about this deletion map I told you before. Of course, there is one more information. You cannot rebuild the index with online option. It's not possible with cluster Columnstore index. Okay, as we have only 19 minutes right now, we should go to the extended events. We have 13 extended events that are very important for us. To me, there are 4. So I was interested in being informed when tuple mover is starting and finishing compressing the data. I would like to be informed when an index rebuild is issued, that's the 3rd. And of course, from the performance perspective, I would like to know how my column store segment elimination look like. You know, sometimes it's not possible to read the log, but it's always possible to run the extended event session. Okay? So, I have a table. I have already a table. And you remember the data distribution in the table from the very first demo. And I would like to run a query that should take data only from this region. So my extended event should give me information that it already eliminated those segments. That will be the goal of the extended event session. So I'm trying to create an extended event session. I'm adding the event there. And I have to store the event data somewhere. So I'm throwing into a file to a disk. And I would like that the latency was around 1 second. So creating the event, extended event session, starting right now, doing the query. I think it's already done, yes. Stopping the session, and let's check how many events we have in my file. So system function file target read file gives me information that there is 39 events in it. So 39 elements were eliminated on the metadata level. So what to do next is to load the data into some temporary table, and you can play around with the XML. What I found is that there are some information in it, for example, when the event took place, what row group ID was touched, and what row set ID was touched, and check the value of it, and you will see some information about that. But we can also have this information from the SQL Server log. But I think that automated monitoring should employ the extended events rather than reading the error log. So that's all about extended events we can do. More interested events, as I told you, when a tuple mover start and ends, and when we have a rebuild, and the last event when we are building the cluster Columnstore index and we have low memory. And this topic greatly moved me to the last point, because we have only 15 minutes, about deep internals of this. So, do we have any DBCC comment on the cluster Columnstore index? We all know and we like the DBCC command we can do on the traditional row store. So for example, dbcc page, dbcc int. Do we have something similar in column store indexes? Where is my memory? What about memory grant? What is the memory grant needed to build a column store index? What about memory pressure? How the system behave? What should we expect? And at the very, very end, what about transaction log usage? So we have 15 minutes, so we can go there into the internals right now. Okay. The DBCC was described by Dmitry Pilyugin on his blog. Unfortunately, the blog is in Russian. I could read it because I know this language somehow. But apart from the comments, it's very hard to interpret the results, yes, but I was able to do so. So there is an undocumented, of course, command which is called dbcc cs index, column store index, which gives you some information about the internals, how the index is stored. First of all, you have to pass the database name or database ID. Then you have to tell about which partition you would like to examine, so Hobbit or partition ID. Then which column ID you are interested in. Column ID means segment. Then which row group, column ID, which row group ID you are interested. Which object type. We have segments and dictionaries. We can check both. And there is the print option 0, 1, or 2. And some start and end parameters, which I did not understand yet. But, okay, let's create a table. Let's create a clustered index, load some data into it, and let's try to issue the comment, the dbcc comment. So I need to know this partition ID to put it here. I have to take this database ID to put it here. I'm interested in column number 4 because this is the ship date key, which is my favorite column recently, and I would like to examine the segment number 0 in that moment. So what is the database ID is 10, and this is the partition ID. So let me copy it here. Trace flags 3604. So we can see data here in this messages tab, and see. Have you ever seen this cluster index from inside? Nothing special, believe me or not. Nothing special. So what is important for us and what I could read is that there is a minimum data ID. So this is the minimum value from this in this segment, the maximum value. This is the situation when the data is not sorted in the index. This is the row count, and this is the on disk size on the disk. So it's around 1 megabyte right now. And you see the encoding type number 2 means that this 1 million rows, this around 1 million rows is still open. It's an open delta store, I think. And some other information that right now are not documented and, let's say, not readable, very, very readable. But I show you in a moment how you can go deeper and deeper using the traditional commands. But to do so, we have to go to the memory. So there is a new memory clerk, which is called Columnstore object pool, because the concept is that we have a traditional buffer pool, which is AK memory pages that are fed from any allocator. Please remember that this memory structure changed in 2012. So we have any page allocator right now, 8K pages. However, the column store object pool is large pages, uses large pages. And the large page chunk is from 2 up to 16 megabytes. So it's no 8K pages anymore. This is very important. When you are loading data to memory that are loaded, the data are loaded, compressed into this column store object pool. But if you would like to do a query, essentially, you have to uncompress the data. So the data uncompressed are stored in traditional buffer pool on 8K pages. And if yes, I can go to the buffer pool and issue normal dbcc page comment to show you how the data are stored internally by the index. And this is what I'm going to do. So we have, let's check to the memory cache counters. Right now, to this view, which give you some information how large is our buffer pool regarding to the cache, to the Columnstore object. And you see I have right now something about 36 megabytes used by my Columnstore pages in memory at the moment. There is another view which is called memory clerks, which gives you information which clerks are currently active, gives us the same, very similar information that I have 36 megabytes right now, and the memory is on the node number 0, which is the only node I have on my laptop. Undocumented view, which is called DMOS memory broker clerks. We have only two. One is related to traditional buffer pool, and the other is for Columnstore. So right now you see that my classic buffer pool uses half gig of my memory, and this Columnstore uses around 40 megabytes right now. So very, very detailed information what sits in the cache about every entry, and description of this was done by Nico Neugebauer, who checked what could be the object type, because now you can query what really is in the memory, so the partition ID, the column name, the object ID, what is the size, how many pages it have, and also Nico found what those numbers are, so described those numbers on his blog. So number 1, this object type number 1 means that this is actually a segment. Number 2 means that this is a global dictionary. Number 4 is a local dictionary. And number 6 is something that is not in any dictionary yet. It will be in some dictionary. But please remember that if you created a row group, which is compressed, you cannot change the dictionaries, at least the global dictionary. Okay, and the very, very familiar view, I think you know about this, is DMOS buffer descriptors, give you information what pages sit in the buffer pool, so we can see what pages are related to our Columnstore indexes. So I could pick a page, and I can try to crack the page for you right now, DBCC, how it was, page. What's the first thing? It's the database, a file, a page, and a print option. So we can see what is on specific page of our cluster Columnstore index when it's loaded into the buffer pool. So you see it's very, very familiar structure. It's at 8K page. But let's go to details where they are. Now, right now, we see that we cannot read anymore something from the page. Everything is compressed, so very hard to interpretation at this moment. But we can go further. What about memory grant? If you would like to create a clustered index, you have to have a proper memory grant on your box. So the mathematic formula is something like this. I don't know who created it, but it works. So 4.2 times the number of columns you are going to use in your cluster Columnstore index, plus 68, multiplied by maximum degree of parallelism you can use to create the index, plus number of columns which are text, multiplied by 34. Okay. If you do not have memory like this, you can't create the index. You will see an error that you could not get memory grant because it exceeds something like this. So please employ resource governor. There is an option when you create a workload group, you can specify request max memory grant, which is typically 25%. So try to make it 50% or 70%, and you will be able to create your index then. But if you don't want to do this, the only thing you can do, or the optimizer can do, or the engine can do, is to lower the DOP level when you create the index. So even if you specify create the index on DOP 8, if it's not enough memory for you, the engine will lower down the DOP, because it's the only thing it can control in this mathematical equation. Everything is behind it. So if you do not have memory, the system will lower down the DOP up to 2. Or if it's not enough, then these segments will be smaller. So no magical number 104856776, sorry, but the segments will be smaller because then it needs smaller grants to create. You can test it. We have only 5 minutes, so I don't want to do this. You can test it if you wish. So create a column store index, then lower the memory, create the index one more time, and you will see that probably some of those operations will go on lower number of cores. What I'm going to do is I'm essentially going to lower my maximum server memory. I'm going to clear the cache, show you what's in the cache, showing you what's in the cache. So right now my only buffer pool takes 11 megabytes. And what I'm going to do is I'm going to do some pressure on my system to load some data into the Columnstore buffer pool. And after it's done, what I'm going to do is I'm going to do some external pressure on my system. So I'm going to start this file, which this is in Polish connection. So connection 1, connection 2. I know what it's all about. So I'm going to start 4 sessions. Each session open a new connection. There will be 2 queries. And the query, you know, it's not very, the query is something like this. To really do a pressure, I'm taking large fact table, do cross-join and cross-join, just to burn out the memory, to see what happened with the buffer pool. So I have 2 such queries here. This is even worse, because it's 30 million rows in each of the table, so doing it 4 times cross-join, it's really huge query. So let's check if we have our data loaded already. Okay, let's check the buffer pool. So now you see that something is 20 megs of data is in our Columnstore object pool, and around 200 megs is in our buffer pool, in our classic buffer pool. So in situation when I start the pressure, I hope my server will survive it. We'll see. I should see, because I don't know if it works right now, that this Columnstore object pool will be lowered down to some very, very low level. Because I don't know if it works at the moment. No, it went up for a moment. But if we stay, or if I create again a pressure, and once again I try to do this, so it can occur that at some point this memory will go down. Because what the system can do, essentially, if you think about this, there are 2 buffer pools. So which one of those is more important to the SQL server? The classic buffer pool. So this buffer pool must be healthy. So if there is a memory pressure, your Columnstore object store will be lower, down and down and down. So everything you prepared in memory will be thrown out. So, okay. Last point, because we have only 2 minutes. First of all, I try to kill the processes. Okay, close all windows. Maybe I can. Okay. So the server should be alive right now. So you can try to play with my scripts to create a pressure in the system. Last thing is transaction log. So I'd like to show you how the transaction log looks like when you create cluster column store index. So I create a table. I'm cleaning the log right now because I'm in a simple mode. So create a cluster column store index on that empty table, and let's check the fndblog function. What's important if you would like to filter using allocation unit name? So traditionally, you have to specify a table. If you are using cluster column store index, you have to specify a table name plus the column store index name to see what sits in the log. So to create an index is only 4 operations. We have to go to the page free space to allocate some page. We have to create an index allocation map and nothing more. And this is the address of the index allocation map we created. So if we load some data right now, we are loading 10 rows. So in terms of these operations in the transaction log, what can we see? We can see only those 10 entries. This is really entering data to the clustered index, and there is also preparing the page. So we have to create a new page to store those data, and you can see this is the address. So 869, we can go to the page. 869.980. And we should see that there are 10 rows in this page. This is row number 1. This is row number 2, etc. And we can go to check what's inside the page. So please remember that in terms of log, creating an index is a minimal logged operation. So don't worry about your log. It will not be burned out when you create an index. And that's basically all what I would like to say to you about this cluster column store indexes. The last thing what I'd like to show you is the resources. So great resources. At first place, Nico Neugebauer, who did 49 posts about column store indexes, cluster column store indexes. So please visit his blog webpage. Benjamin Nevares and Paul White, which describes everything in great details about processing, about internals, about optimizer. Remus Rusanu mentioned about service broker and other things, also column store. Hugo Cornelis, who is with us, who did a great talk yesterday, and of course Joe Seck from SQL Skills, who also has great posts about the column store index. So once again, thank you for coming, attending for this session. I hope you enjoyed it. So I wish you a pleasant stay here in Copenhagen and the rest of the conference. Thank you very much.